Okay. Let's go back to example 1. Were there any questions that I missed earlier that folks would like me to go back and address?
I had one quick one on
Okay, sure. What's up?
that. So, someone asked that what if you did the u sub for the x cubed,
Uh-huh.
and then when you sat there and you took the derivative, you got 3x squared.
Yeah.
My question is that if you got to a point like that and you took a second derivative, when you plug that back into the integral, would that mean that you would have to take the second integral when you plugged in your du back in there, or is that even like a thing?
There are double and triple integrals, yes. So that is a thing, and that is a really big thing in Calc 3. Um,
Okay, I'm
as
not
far
worried about that.
Yeah, as far as the limitations of what we're doing now, we're just dealing with a single integral and how can we match that du or the dx. So we don't want to get ourselves in deeper than we need to.
I ain't trying to.
Okay. Were there any other questions on 1 or 2 that folks wanted clarification on?
And then I had one more on example number 2.
Okay, sure. Go for it.
You know how you have the square root of x, and then you have the cube root of x.
Yes.
Let's say that you had an expression where you had a parentheses and you had a polynomial in there, and then right next to it you had a square root with the same polynomial in there. Would you still treat it the way that you did here, where you would give them both fractional exponents and then start messing with the u? So like, let's say you had parentheses x plus 2, then next to it you had the cube root of x plus 2, and that was on the bottom.
And are they connected by addition, like here?
No, I think that they were connected by multiplication. So if they're connected by addition, then you go through this whole route right here.
Right, right.
But if
Yeah. Are you talking about one of the quiz questions?
yeah, because I saw on number 7 it was something like that. So I'm wondering that when I go to the quiz, if I'm gonna have to start doing stuff like this.
No, I think it's a little bit. I think they're a little bit more straightforward in terms of like you're not going to need the synthetic division part, but we can certainly at the end of class maybe at least set up number 7. I know I got a few other questions on number 7, so.
Okay.
Okay, cool. All right, any other questions on number 1 or number 2?
I do have a question.
Okay.
About the synthetic division, you need to start from, I just forgot how we do it. You need to start from -1 because you had the y plus 1, so you needed -1?
Yes, so it's whatever makes that denominator equal to 0.
0. Okay, thank you.
Okay. All right. So let's go ahead and take a look at example number 3 and 4. Okay. Now these are very specific cases. Okay. So once in a while, you'll see a situation where you have a sum or difference of sine and cosine. Okay. And so we can approach this one actually in 2 different ways. All right. So I bet some of us could see maybe one way to do this. And that might be to think about like a Pythagorean identity here. Okay. Now, if this said 1 minus sine squared instead of 1 plus sine squared, if that were a minus sign, then I would 100% replace that with cosine squared. So then I could reduce from there, okay? But since it's a 1 plus sine squared, it's actually not one of the Pythagorean identities, all right? So what we're gonna do here is actually do a pretty straightforward u substitution, all right? So I'm gonna let u equal to
ix.
Yeah. Sorry. Okay. U equal to sine x, and then du equals cosine x dx, right? And when we substitute all of that in, we'll end up with the integral of 1 over 1 plus u squared du. And that we definitely want to know for tomorrow is a very classic case arctan. And in this case, our a equals 1. And so what we get here is the arctan of u plus c. And then we have a few different ways that we could finish this off, but I would say the most straightforward way is simply to take this u and replace it back with your sine x. So a very traditional u sub. And that would give us arctan of sine x plus c. Okay. All right. Any questions on number 3? And yes, that's it. That's it for question number 3. The cosine x in the numerator got substituted out when we did our du. So cosine x dx, everywhere I see the cosine x dx, I'm going to replace that with a du. And so that becomes just the du on the end.
Just to make sure, if we were to have like, instead of 1, 4, the a will be 2, right? And then we'll take that a out into a reciprocal, like 1/2 times tan arctan u over a.
Yes.
Okay, so make sure.
Exactly. Actually, I'm going to write that out in case folks didn't catch that. So Karen asked a great question, like a what if? What if you had 1/4 plus u squared and you were trying to find that integral? Then your a is 2, not 4. And the way that comes out in the answer, it's 1/2 arctan of u over 2. Okay, so it's exactly like you said, Karen.
Okay, thank you.
I have a quick question about the arctan formula. If you have like a number or a coefficient in front of the u, you're supposed to factor it out, right?
That's one way, or I think there was a formula where we, actually, yes, you want to factor that out. If you do the if you do the trig sub that we did in 9.3, we did one example where there was a coefficient in front of the x squared part, and that ends up just being part of our substitution. It adds to the coefficients, or it's included in the coefficients, but I don't think you're going to see stuff like that tomorrow on the exam.
Oh, okay, thank you.
Okay.
Question.
Hold on one second. So Carlo, if you're looking, is it the reciprocal? It's 1/a. 1/a. So yeah, you could say the reciprocal of your a value, or 1/a. Okay. Okay. Sorry, who did I interrupt and what was your question?
At what point with these types of questions do we go back into drawing the triangle?
Good question. I would say that in this case, I would not draw the triangle because all I want to do is get back to a situation where I have an x in my answer. And because I already have u equals sine x, I don't need to draw a triangle. Like I already have it in terms of x, if that makes sense. Like the substitutions we've seen are like x equals like 3 sine theta, right? So like we get an answer in theta, but we need it in terms of x. All right, Mariah, did I lose you or did that make sense?
Yeah, that's good.
Okay. Yeah, when we have the trig sub with theta, then we use the triangle. That's a great way of summarizing that, Sean. Okay, so if you see a theta, then you're thinking, okay, I need a triangle. But in this case, you don't need the triangle. All right, so our end goal is always just to get it back in terms of x, and so we want to do that in the most streamlined way possible. Okay. All right, so let's get through example 4. Hope I don't run into any more technology issues. Okay. But before we get to example number 4, and again, this one is a very specific case. So I just wanted to show you one, but there are situations where you end up with sums of sine and cosine, and because they're both in the denominator in this case, like it's not easy for us to use a u sub, because our u is going to be in like a traditional u sub, because our u is going to be in the denominator, and so would our du, but that doesn't really work out for us conceptually. Okay, so these are very specific substitutions, and so this might be helpful in answering some of those quiz questions. And what we have here is a few special rules. Okay, so if an integrand is a rational expression, and a rational expression means that there's some sort of fraction involved, okay, involving sine and cosine, then the following substitutions will produce a rational expression in terms of z, okay? So sine x could equal 2z over 1 plus z squared. Cosine x can equal 1 minus z squared over 1 plus z squared, and then that gives us a dx of 2 over 1 plus z squared dz, okay? Now, one thing I am going to do, I'm going to use u's instead of z's, because my z's sometimes look like 2's, and I don't want to confuse myself or you, okay? So instead of a z, I'm going to write u. All right, so we can think of this as a very, very specific case of a u sub, all right, where they're telling you what to plug in. So let's try this in our particular example number 4, and see where this goes. Okay. So the first thing I'm going to do is I'm going to apply the substitutions that are there. So I'm going to get the integral of 1 over the 4, but instead of sine x, I'm going to write 2u over 1 plus u squared. Minus 3, instead of cosine x, I'm going to write 1 minus u squared over 1 plus u squared. And then I need to replace my dx with 2 over 1 plus u squared du. Okay. So all I've done is take the substitutions that they told me to put in and just plug them in. Okay.
I have a question about that part.
Okay.
What do you mean that they told you to put in?
Well, they said everywhere you see a sine x, you're going to put 2u over 1 plus u squared.
So that's specifically only for that question, just because they told us. That was the instructions, right?
Yes, like anytime the questions look like example number 4, then you use this rule.
Okay.
Okay.
So every time that the sign will be on the bottom?
Sine and cosine. Yep, we're looking for sums and differences of sine and cosine.
Okay, thank you.
All right, so that sign came from there. The cosine one, 1 minus u squared over 1 plus u squared, gave us this. And then we wanted to make sure that we also got a dx to replace. And so that's why we put this green part at the end. okay? So I don't have the quiz pulled up in front of me right now, but there should be a couple questions that kind of look like this format, and that would be a great time to use these formulas, okay? So for example, like question number 9 on the quiz. All right, question number 9 would be a very good time to use these particular rules. Whereas question number 8, I think you can use a regular U sub for question number 8.
Professor, just to clarify, we only use this one when the sum and difference of sine and cosine is on the denominator?
Yeah. Yeah, so when we're looking at like rational expressions. All right. So from here, we're going to do a whole bunch of algebra, okay? We're going to try and simplify this pretty ugly looking fraction. What do we replace the u's with? We're going to work through the entire problem with u's, and then at the end, we're going to put that back in with the x's. And here's what we're going to put back in. Everywhere we see a u, we're going to replace it with tangent of x over 2. Okay, really great question. I love that you're thinking ahead. Okay, so here's what I'm going to do, okay? I'm going to distribute this 4 to that fraction, the 3 to this fraction, okay? And then I notice that this denominator in the blue fraction is the same as the denominator in the yellow fraction. And so once I distribute, I'm also going to write this as a single fraction. So I have 1 over 8u minus 3 plus 3u squared over 1 plus u squared times 2 over 1 plus u squared du. Okay, so again, to get that new fraction, because they have the same denominator, I was able to combine them into one fraction, and this minus sign became a plus sign because I had to distribute a -3. So the -3 times the negative u squared gave me the positive 3u squared. Okay. Now, let's look at this right here, okay? So the definition of a reciprocal is that it's 1 over the thing. So when I have 1 over this fraction, it's really the same as the reciprocal of the bottom, which is 1 plus u squared over 8u minus 3 plus 3u squared times my 2 over 1 plus u squared du. Okay, so again, that 1 over just means the reciprocal. And what that allows me to do is reduce those two pieces. And so I end up with 2, because I'm going to take that constant out to the front, the integral of 1 over 3u squared plus 8u minus 3 du. Now, I want to pause here for a moment because the question for you is completing the square or partial fraction, okay? So take a moment and see if you can figure out which one you're supposed to use. Because if it's partial fractions, you should be able to factor that denominator. If it's not factorable, that means that we're going to go with completing the square, okay? All right, I hear 1 completing the square. Anybody else have other ideas?
Because it's not factorable.
Completing the square. This one is actually factorable, all right? So I think that's one of the things that you really want to make sure that you brush up on is your factoring skills. And I know that a lot of us not a lot. Some of us have like been like, I don't like factoring, so I'll just use quadratic formula, and I hate factoring when that first number isn't 1, but it is a reality that we need to be fluent with that, okay? So this denominator does in fact factor into 3u minus 1 times u plus 3 du. Okay, it is factorable, which means we're not using completing the square, but we are going to use partial fraction decomposition. Okay. All right, so let's take care of this partial fraction decomposition, some good practice for tomorrow, all right? So partial fraction decomposition, we're gonna get 1 over 3u minus 1 times u plus 3 equals, let's see, both of these are linear, none of them are repeated, so it's our very basic case, a over one denominator plus b over the other denominator, right? Now, I'll give you a moment here to kind of set this up, see if you can solve for A and for B, all right? These are not as messy as the ones in the quizzes, but I do want us to, you know, get some extra practice in the partial fractions before tomorrow, okay? So set up that equation, what does it look like, and let's get some values for A and B. Right, we should be getting b equals a, whoops, -1/10, yeah? And the other value that might be nice to pick for you would be a 1/3. Right, so we're getting two fractions, a -1/10 and a 3/10, but they have the same denominator, okay? Any questions about finding this A and B? So from here, I'm going to go back and rewrite my integral, okay? So my integral is going to have a 2 in front, and it's going to be 3/10 over 3u minus 1 minus 1/10 over u plus 3 du. Okay. Let's split that into two integrals and pull all the constants out to the front. So I have a new coefficient of 6/10 for the first one, 1 over 3u minus 1, minus 2/10 the integral of 1 over u plus 3 du. Okay. Now, when I look at these integrals, all right, I'm thinking natural log. But this is a mistake that I've started to see on some of the quizzes. One of these, it doesn't really matter if you do u sub or not. You're going to get the right answer. But the other integral is going to be one where if you don't make a u sub, your answer is going to be incorrect. It'll be off by a factor, okay? which one do I have to do a u sub for?
The 3u minus 1.
3u minus 1.
Perfect, okay? So that's really something we want to keep on our radar, that this one you need to use the u sub. Your v is 3u minus 1, dv equals 3 du. So you should have an additional 1/3 multiplying factor in that first integral, okay? If you forget to do it for this one, it doesn't really matter because v equals u plus 3, so dv will just be du, right? You're not missing a factor. But when that coefficient's not equal to 1, you want to make sure to do that u sub, okay? So let's put those all in and see what we get. We get 6/10 times 1/3 the natural log of 3u minus 1 minus 2/10 the natural log of u plus 3. And let's go ahead and reduce some fractions. So 6 and 3 reduce to a 2 on the top. And then this 2 and that 10 reduce to a 1/5. And this 2 over 10 also reduces to 1/5. And so we'll get 1/5 natural log of 3. Now instead of u, I think it was Patrick who asked this question, what do we have to put back in so we get our answer in terms of x's? You don't need a triangle, but everywhere I see a u, you're going to put tangent of x over 2. So 3 tangent of x over 2 minus 1 minus 1/5 natural log of tangent x over 2 plus 3 plus c. Okay. So there we have our very special case situation, all right, where we're looking at a very specific substitution. But I think the more important part here is knowing that at some point you might need a partial fraction, and I did want to review that again before tomorrow's test, okay? So just kind of highlighting some of the most common mistakes that I've seen on the quizzes, all right? So if you've made some of these mistakes, you are not alone. I bring them up because I see folks consistently who do these, okay? So I just want to make sure as we head into tomorrow's test that we're feeling, all right, these are things I know I need to look out for. And so hopefully we won't make those errors tomorrow, okay? All right, so. This is it for today's class, all right? I know there were some folks who had a question on number 7 on the quiz, so I'm happy to start there. And if you want to stick around, you're welcome to stick around and ask more questions on quiz number 3. And if not, have a wonderful rest of your day, and I will see you folks not tomorrow, but I will see you on Thursday at 9:30, okay? You're welcome.
I have a question. So will the quiz that's due on Thursday, Friday morning, is that over just 10.1?
Yes, ma'am.
Can you scroll down to the answer of this problem?
For sure.
Thank you.
This answer?
Yeah, thanks.
Mm-hmm. Yeah, I'll give folks some time to finish copying that down, and then we'll take a look at some of those quiz questions, all right? So we'll start with number 7. Are there any other ones on folks' radars that they're like, ooh, I definitely want to go over this one before, you know, we have
number 4.
Number 4, okay, so number 7, number 4, 5, 15, 4. Okay.
You might be able to just answer this with a yes or no.
What's that?
You might be able to just answer this question with a yes or no. But on number 8,
Okay, on the quiz.
you see that denominator? If you distribute that out, then we can use the method that we just used right here, right? Where you plug in whatever you see for it, because it's the difference of cosines.
For number 8, I think I didn't try it that way, so I have to get back to you on that. But I think for number 8, it might be a better idea just to try a more basic U sub.
Okay.
Yeah, so like U is, what's the trig function on the bottom?
Cosine x times cosine x minus 1.
Yeah, so I'd let U equal cosine x.
Okay.
Okay. All right. Is it okay if I leave this screen and take a look at and pull up quiz number 3?
Definitely.
Okay. Quiz number 3. All right, so number 7 was first on the list, I believe. If I get this out of order, I apologize. But let's take a look at this question, okay? So this is definitely like a less traditional U sub situation. So in this case, I let U equal the whole radical, okay? And the reason why I did that is because if you let U equal the radical, it'll be easier. You're sort of bumping all the powers up by whatever factor. So the power for U is 1, and this one is a power of 1/2. But I know for me, like 1 is an easier power to work with than 1/2. So that was my reasoning behind making this part my U, okay? And then I used one of the strategies that we talked about in class today, where you can algebraically solve for x. And so in this case, I was able to square both sides. So I got U squared equals x minus 2. And then I know that I wanted to match it with x plus 1. So in order to get this minus 2 into a plus 1, I had to add 3. And if I add 3 to the right-hand side, I must also add 3 to the left-hand side. So what I get is everywhere where I see the x plus 1, I can replace it with U squared plus 3. Okay? And then I take my derivative from there. So 2u du equals dx. It makes my derivatives easier. And when I plug everything in to my integral, right, everywhere I see the x plus 1, I put the u squared plus 3. And everywhere I see the square root of x minus 2, I put the u. And to be thorough, everywhere I see the dx, I put a 2 du, and so that 2u du, so that went here. So I've substituted everything out. And what happens is I end up with a situation where it looks a lot more familiar, okay? Specifically, I look at this and I'm thinking, ooh, arctan. And all the powers are no longer fractional powers, right? So I don't have any square roots mixed with whole number powers. Everything is just a whole number power. So from here, hopefully it's pretty straightforward. I think it's the toughest part of the setup, but we definitely want to start thinking that this is the arctan with a equals not 3, but the square root of 3. And like that great question from earlier, how does that impact our integral? We have the 1 over a and the u over a. So that's where that factor is going to come into play. Okay. Now in this case, I did not need to draw a triangle because I had my u directly linked to an x. So at the end, I was able to just put back in square root of x minus 2 in for every u, okay? Does that help with the setup and solution for number 7?
Yeah, I think the difficult part is just when you look at stuff like this, there's so many other off branches that you can take that I think just with more practice, it'll help us with our decision making at the beginning of how we want to approach it.
Okay. All right. Let's see. There's a question on number 5. So let's head back up to number 5. Is it okay if I scroll back up?
Yes.
All right, so question number 5 here. All right, so question number 5 was definitely a completing the square, because in this case, the denominator was unfactorable. Okay, it's unfactorable. So this is a really good example of when we think about factoring out a greatest common factor from just the first 2 terms, okay? So this 4 I pulled out from both terms, so I ended up with x squared minus 2x there. Now, as our conversation yesterday, that 4 is going to impact our, it's going to impact the number that we add or subtract to the end, okay? So if I do the completing the square, I have a negative 2. So negative 2 divided by 2 is negative 1. And negative 1 squared gives me a positive 1, okay? But as we see over here, this 4, I need to multiply that, because I didn't just add 1, I added 4. And since I added 4, I need to accommodate for that by subtracting the 4. And so that gets me to a situation where I have something like this, 10x over 4 parentheses x minus 1 squared plus 5 dx. Right? Now at this point, I chose to make a u sub as x minus 1 equals u, so that I could get it more into a structure that just has less moving parts to it, okay? So when I made the substitution, it gave me 10u plus 1 on the top over 4u squared plus 5. And what I was able to do from there is distribute that 10 to both the u and the 1. And then a technique that we've learned a couple days ago, we split it into 2 fractions, and each fraction is going to require different strategy. So the first fraction is a case where we could use a u sub, and the second fraction is a case where we can use arctan, okay? And whoever asked this question earlier, very spot on, that we need to factor that 4 out as the coefficient for the u squared in order to use that arctan, okay? I don't believe you'll see any of those on the exam tomorrow, but I did want us to get a practice one in on the quiz, okay? So we factor that 4 out, so this 4 moved out to the front here, okay? From there, I think it's probably sort of the home stretch in terms of finishing up with doing our u sub, and we end up with a natural log, and then doing the arctan and making sure we just keep track of all the coefficients. I think that's probably the most challenging part after we get through the setup, okay? Does that address questions for number 5?
Question on the algebra for that coefficient for the arctan.
Okay.
Shouldn't substitute to 5 over root 5 instead of root 5?
5.
Or am I just missing something?
You mean at the end here?
Mm-hmm.
5 over root 5 is root 5.
Okay.
Yeah. It's kind of like if we did it with a non-fraction, 9 over the square root of 9 is 9 over 3, which is 3.
Okay.
Okay. All right, let's see what was next up on the list, I think was...
Is that because you want us to rationalize it?
No, it's, you don't, I mean, you could write it as 5 over root 5.
Would you take out points for that?
No, I wouldn't. I think it's more, it kind of depends how far you plan to go in math. Like, I want us to be familiar with some other things that other professors are potentially picky about. But if you left it as 5 root 5, that would be fine. I think especially this chapter is so algebra heavy that let's focus on, like, you know, the decision making, like how are we taking these integrals and then going from there.
Okay.
Okay. All right, next up on the list I have is number 15. So let's kind of scroll down to the bottom. So the last few questions here are meant to be like a mixed review, okay? So I know a lot of the quizzes have been like this section and then this section, and this one, I took a couple questions from 9.5, a few from 9.6, and then I left the last 5 to be like a mix of all the different strategies we've used so far, okay? So let's take a look at number 14. All right, so number 14 is a, wait, no, sorry, number 15. Number 15, so in this case, we're looking at what might be a good U sub to make, okay? Now, I think this goes back to just remembering the idea of the chain rule. Okay, and I know we haven't seen chain rule in a while, but chain rule is like, chain rule and U sub are essentially the same thing. So chain rule is for derivatives, and then U sub is how we figure out where this chain rule came from, okay? So when you first learned U sub, one of the strategies I hope you learned was that the things that are raised to the power tend to be the U. And so in this case, what I mean by that is that this 1 minus cosine cubed theta is raised to the power of 10. So that's probably a good thing to try for the U, okay? Now, it might be kind of intimidating because you sort of have this whole other piece here, and you're like, how am I gonna get rid of all of this? But if you take your derivative of 1 minus cosine cubed theta, you get, let's write it like this, 1 minus cosine cubed theta is the same as 1 minus cosine theta cubed, okay? And so when we take our derivative, the 1 goes to 0. We don't have to worry about that part. However, I have this negative sign, and I have one function inside of another function. And so that is an immediate, like, oh, it's going to be chain rule kind of situation. So chain rule says we take the derivative of the outside part. So 3 cosine theta squared, all right? And we don't change the inside. And then we multiply that by the derivative of the inside. So the derivative of cosine is negative sine theta. And when we clean this all up, we end up with a negative and a negative, make it a positive 3. And we traditionally write powers of trig as the power inside there. So cosine squared theta, sine theta, d theta. And it turns out the only thing we need to do to match it with whatever's left in our integral is to do du divided by 3. Okay, so that's where I get that 1/3 from. And believe it or not, all that algebra in the beginning means I only need to use power rule to set up this, or to solve this integral. Okay. Charmaine, does that answer that question? And Mariah, I think you both had questions on here. Okay.
I think I was just panicking because of all the powers.
I know. And I think honestly, that's the worst thing about Calc 2. Like this unit is like, there's so many different ways. And we don't always have a lot of time to dive deeply into every single method, you know, but algebra can definitely get you pretty far.
And then also, Professor, you just went over 5. I just wanted to confirm, we factored out a number from the denominator on number 5. It's the same process for number 4, right?
Yeah, that was the next one up on the list, is number 4. All right, so for number 4, exactly. So we see here that we have a 2x squared. And so it's going to be in our interest to factor that 2 out of the first 2 terms, okay?
Oh, yay.
So now this one I wanted to put in here because it's got some fractions. It's good for us to just like build up that kind of, you know, gusto with our math, be able to accomplish these fractional things in the middle of problems. So I just wanted us to have an example there. But once we factor out that 2, the entire process is very similar to number 5, okay? The numbers are just maybe a little bit less nice.
I think on this one, I thought I was doing something wrong because I ended up with like 63/8.
Yeah, 60.
So
okay.
kind of stopped halfway through, and I was going to ask you if I was going down the right track, but
Yeah. All right.
cool.
Yeah.
Thank you.
You're welcome. All right, it looks like we've got a question on 14 and 12 as well. But for the folks who asked about number 4, does this kind of clarify number 4?
Yeah. I was confused because I saw the denominator in the last part, and I didn't know if I needed to factor out stuff. So.
Yeah. I think part of this is like, and I think honestly that's one of the biggest things that you learn from pre-calc is that it's okay for things to look weird. It's okay for things to not have whole numbers and things like that, okay? All right, so let's go ahead and scroll back down to number 12 then. Okay, so let's go back and take a look at number 12. Okay, so your question for number 12 was this one. I think someone also asked about this one. And if we take a look at this, okay, when we were learning 9.3, we saw a bunch of stuff like this. And then since then, we've learned so many other techniques that it's kind of like, well, which one do we use? But number 12 would be a case where we could do a trig sub, like from 9.3, because we're looking at that x squared plus 4 squared, or x squared plus 16. And so we can put in, everywhere we see an x, we're going to put in 4 tangent theta. And then everywhere we see a dx, we can put 4 secant squared theta d theta. And because I'm setting up the trig substitution, I went ahead and set up the triangle as well. So I know what my substitutions are going to be at the end, okay? After that, we moved through a bunch of simplifications, but one strategy that can be helpful sometimes when we're trying to determine can we take an integral or not is going back to this idea that everything can be written in terms of sine and cosine. Okay, that's one way to look at it. Sometimes when you write things in terms of sine and cosine, it cancels some stuff out, or it writes a trig function in a way that is easier to take a integral of, okay? So with a few simplifications, I was able to get this to be 1 over sine squared times cosine theta d theta. And then that allowed me to do a u sub where I had to use power rule. And then I didn't need to use any other of the trig identities for number 12. Callie, I'll get to that question in a moment. Maybe let's scroll down for number 14 and then we'll take a look at number 1 again, okay? All right, does this kind of clarify the setup for number 12? Let's take a look at number 14. Okay, so 14, again, we want to see like, can we factor this? Can we not factor this? And additionally, even if it's factorable, if it's inside of a square root, completing the square is usually the better option, okay? Because when we have that square root, we can't necessarily split it into the partial fractions. That makes it a little bit harder, okay? So two things to look for here. Is it factorable is one question, but if there's a radical, you probably want to use completing the square. Right?
Yeah. Oh, sorry.
What's up?
Do you think we can go over like how you created the triangle again? Like the setup?
Yeah, let's do that and then we'll go back up to number 1, okay?
Perfect.
Okay, so this part right here, yeah, like when we set up our substitution, that helps us with the triangle.
Okay.
I made my answer key before I suggested that technique in class, which is why all my triangles have are at the bottom. Okay, but I'm going to take this first line where I have x plus 2 equals u equals 4 secant theta, all right? And I'm going to get rid of that u. I want to go ahead and just put everything in terms of x. So x plus 2 equals 4 secant theta. And that means that secant theta equals x plus 2 over 4, right? Like if we think about that algebraically, we're just moving the 4 to the other side. So we're isolating our trig function. Whatever trig function you have, if you isolate it and you think back to what you know about SOHCAHTOA, all right? So cosine is adjacent over hypotenuse, but secant is the reciprocal of that. So the top represents the hypotenuse and the bottom represents the adjacent.
Okay.
Okay, so you go back to SOHCAHTOA. That's how we know which sides of the triangle those represent.
Right. Okay.
And then you just fill in your hypotenuse, your adjacent, and then.
Okay, perfect. That helped a lot. Thank you.
All right, cool. Okay, so let's see. Let's go back up to question number 1, I believe. Is it similar to number 3 in the notes? I don't know. Let's see. Okay, so number 1 here is a completing the square one, okay? So there's no radical, but if you're thinking about how to make that decision, it's the can you factor it or can you not? And this x squared minus 2x plus 2 does not factor nicely. So then our option is to complete the square. And once we complete the square, it turns really nicely into an arctan situation. And then we can just, and even in this case, a equals 1, so we don't really have to worry about the dividing by a. All right. Are there any other questions on this quiz number 3 today?
I was wondering if you go back down to 7. I have a question about the second substitution that you do.
For sure.
I can get to 1 over u squared plus 3, but I don't know exactly how to substitute it so that when I back substitute it, it comes out the right way.
Okay, so are you okay at this step?
Which one?
The one with the pink check mark?
I don't see it. Hold on. You might be in the way. Yeah. Okay. Yeah. I see it. Yeah. I'm there and I'm trying to do, what do I substitute u, or what letters do I use when I'm doing the substitution and then the derivative so that I can make sure that when I back substitute, it's all the right way?
Like, is your question, how do you get to here?
Yeah.
Okay. And so the arctan formula, all right, let's just write that over here. The arctan formula is if you have 1 over u squared plus a squared, it's going to be 1 over a arctan of u over a plus c.
All right. So basically what I'm asking is, do you do u equals, what was it? Tangent of u? Or do you u equals like you do u equals √3 tangent of u, or would you do u equals √3 tangent of x, or
So
that's my question.
Oh, okay. So if this is a u right here, then in the next step it's still going to be a u.
Yeah.
Yeah.
Okay.
Okay.
Yeah.
Yeah, and then this u goes back to the square root of x minus 2 because of our initial u sub.
I have a question about number 5.
Number 5, yeah. What's your question?
So the 4 in the bottom, can you use a version of the arctan formula that has the what's it called, the u prime on the top, so that you can just like make that 4 into a 2u squared, and you know that formula?
I do. I would prefer that we kind of work through it this way.
Oh,
if you see a coefficient there.
Okay, thank you.
Okay, you're welcome.
On number 8.
Mm-hmm.
Oh, okay, never mind. I got it right.
Okay, good.
Like I was sitting there and I got to the 1 over u squared minus u, and I just stared at it for like 5 minutes. like trying to think about what we did today in class, and then PFD.
Yep, if it's factorable, PFD.
All right, thank you.
You're welcome.
Professor, for number 7, why isn't it plus or minus square root of 3?
I think that when we're doing the A's, we're assuming that it's the positive one.
Okay.
Okay.
That makes sense. Thank you.
All right. Any other questions out there?
For the setup on number 9, are we going to be using the very last one where you just plug in what it is for sine, what it is for cosine?
Yep.
And then
exactly.
Okay. With that 1, did you turn that 1 into? Oh, you turned that 1 into 1 plus u squared over 1 plus u squared.
Yes, exactly. Because we can make 1 into anything we want. So what's the best option here? As we say 1 equals 1 plus u squared. Oh.
Right on.
Okay. All right, folks. Any other questions out there?
Can I see how to set up number 6?
Number 6.
Yeah, I'm kind of looking at it and I'm at a loss.
Okay. So I think this is sort of a blend of like traditional versus non-traditional U sub. So the thing that's in the denominator or the thing that is raised to the power, and in this case it's both of those, that tends to be the U. So that's why I let the x plus 3 equal U. The less traditional part is like how you get rid of the x on the top, and that's where you have to turn it in, like solve for x, and then you can substitute in an expression with just u's in it.
Okay, I was trying to substitute the entire thing, like
Oh, no.
but that just was a mess. So
Yeah. I know it's a little bit like Goldilocks in the sense that finding the best U to substitute in, it's like sometimes it's too much, sometimes it's not enough, and it's, you know, we got to develop a flexibility to kind of keep trying until we find the one that's just right.
makes sense.
All right, I think I saw a question on number 10, the setup for number 10. All right, so number 10, I would say, is similar to number, is it 8? No, 7, all right? So number 9 and number 7 are kind of similar. The one difference I do want to point out is in 7, there's parentheses around that x plus 1, okay? In number 10, there's no parentheses around the x minus 3. So what we have here, like if I were to rewrite just the denominator, it's x minus 3 times square root of x plus 10. Does that make sense? So the setup is a little bit different because there are no parentheses around the x minus 3. It's really saying x minus this other thing, okay? So then when I'm solving for x in my u, I end up with this whole x becomes u squared minus 10. All right, Lindsay had a question on the setup for number 11. All right, so with number 11, this is a really good throwback to the very first day of class, all right? So your brains have all grown so much since that first day. I just hope they're not feeling too tired at this point, but this is a case where we have 2 different kinds of functions that are multiplied together. And so when we see that situation, we're thinking, oh, integration by parts is when we usually mix and match the types of functions, okay? So this is a good time to think about, like, how do we determine what the u is versus the dv? And remember, we have 2 different phrases. We have the lie8, or we have lipet. Okay, so anytime you see a mix of 2 kinds of functions, the log, if you have a log, that has to be your u. But more often than not, we'll end up with some sort of algebraic or polynomial, and that's going to be your u. Okay, exponentials and trigs are less, not less important, but they have less priority in this ranking system. So that's why the sign for x becomes our dv.
Can I ask one more question?
For sure.
Are you teaching Calc 3 in the fall?
I am not, no.
Okay.
Yeah, I actually haven't had a chance to teach Calc 3 yet, so I'm like, I'd like to get on that list somehow.
I could, well, I have to register tomorrow, and taking a math class this way, I wish it was this way when we switched to online last semester. This way is much more interactive, which is helpful for math.
if you send me a list of, I mean, you guys are all very savvy in terms of choosing your professors. I don't know who's teaching what in the fall, but if you're welcome, Joel. But if you have any questions about like the styles of different professors, I'm happy to give a little bit of feedback on that. Oh yeah, if Bernal is teaching Calc 3, I would 100% try and get into that section.
Thank you.
Yeah, I would say that Bernal is